Going to take you through 14.4 now, kinematic graphs. There's not anywhere near as much algebra in this, so some of you might find it much easier, and I'll be doing it all on the screen as I'll be able to go through Caboodle. As I say, there's not much working out to be done. It's more sort of single word answer or straightforward arithmetic calculation. First of all, I'll go through the PowerPoint and talk about some of the key things you need to know, and then we'll look at the questions in Caboodle. Here I am in the top corner to talk to you about kinematic graphs. Kinematic graphs are graphs that describe movement or journeys. So they can be distance time graphs, or they can be speed time graphs. This one is a distance time graph, and I'll talk to you about what different things on it mean, and I'll look at a speed time graph in a moment. So this is my base point where I start from, and this tells me that I'm going away from it. My distance away from it is getting further. The steeper the line, the quicker I'm going away from it. So my speed is greater. If the line is horizontal, then that means I'm not moving away from it, so I'm stationary. And if the line is coming down that way, it means I'm coming back towards where I started. There you go, heading down is the return journey, coming back to where I started. The crossover from science comes from these calculations here. So you might have seen these triangles. You can work out the speed by doing the distance divided by the time. You can work out the distance by doing the speed multiplied by the time. And that's why it's effectively the speed is a gradient, because I'm doing the change in y, change in the distance, divided by the change in x, the time. So it goes back to those ideas of linear graphs we were looking at. Here we've got the actual question, so I'll take you through some of the ideas here. For how long did the car stop at Denby? Well, we said stop being stationary with those horizontal lines. So here's a horizontal line at Denby. If I count the squares, there's 1, 2, 3, 4 squares make an hour, so each square is 15 minutes. So these 3 squares make 45 minutes. When did the car arrive back at Alton? So here we are back at Alton, because I've gone away from there, had a stop, gone somewhere else, had a stop, come back to Alton at 1700 hours. That's 24-hour clock. If you want it in normal time, then take 12 off the hours. That's going to be 5 o'clock in the afternoon. When did the car leave Denby after stopping? So here's my stop at Denby. So I left there, which is that point there, 15:45, or take 12 off 15, that's 3:45 in the afternoon. Find the speed of the car from Alton to Denby. So from Alton to Denby, the change in y is 20. The change in x is an hour. So I'm doing 20 kilometers divided by 1 hour. So that is 20 kilometers per hour. So we get that 20 kilometers per hour. And that's why we have that slash, because it means divide. Kilometers divided by hours. Now we want to look at Fordham back to Alton. So here's Fordham back to Alton. So this time, if you want to be strictly correct, you could say that's minus, when we talk about minus gradients. But in most cases, you're okay just taking that as a positive speed, because we're not being really picky about what the direction of the speed is. If you're doing a high level of science and looking at velocity, then that would actually count. For this one, we're just looking at the change in y, which is 45, divided by the change in x, which is half an hour, or 0.5. So 45 divided by a half gives me 90 kilometers per hour. Now we'll look at one where we've got speed time. Here we go, speed time 1. So this time they look similar, but this means that my speed is constant. So it doesn't mean I'm actually stopped. It means I'm not getting quicker, I'm not getting slower. So I'm still moving away or going somewhere, but I'm just not accelerating or decelerating. This line here shows that I am accelerating, getting quicker and quicker. When it's going down, I'm decelerating. So I was going at, that looks to be around 11 meters per second, and now I'm going at 0 meters per second. And at this point, that will be stopped. So this line shows that I'm not changing speed. This line shows that I'm not changing speed, but I'm still moving. This one, when I've got down to 0, means I'm not doing any speed, so I've stopped and I'm not moving. This has got a similar triangle, but this time the velocity or the speed is the top one here, and acceleration is the change in velocity divided by the time. So if I wanted to find the acceleration at this point, I'd need to do the change in y divided by the change in x. Hopefully that's given you a reasonable idea of the ideas we look at, and I will now do a few questions for you. So this is 14.S on Caboodle, and we've got a distance time graph similar to the one I went through on the PowerPoint, so I won't talk about it in too much detail. What's the speed between 12 o'clock and 13:30? Or between 12 o'clock and 13:30, I've got one straight line, so the speed is the same, and the change in y is 20, the change in x is 1.5 hours, so I need to do 20 divided by 1.5. That will give you what the speed is in kilometers per hour. What's the speed between 13:30 and 14:30? Well, that's 1 hour. So again, the change in y, which I can see goes from 60 to 20, so 20 to 60, that's 40, divided by 1, that's going to be 40. So this is steeper, we just calculated it is actually quicker, which fits in with what we were saying. Question 4 is a little bit awkward because this is a horrible scale. We've got 2.5, 7.5, 12.5. And it asks me for 12 seconds. 12 seconds is just before that line there, so it's around about that. So the speed looks to be around about 6.5 meters per second. Remember, when we're looking at the speed time graphs, this doesn't mean stationary, this means doing the same speed. So not accelerating or decelerating. This shows me that they're slowing down, coming down to the speed of 0, coming to a rest. This one tells me they're speeding up. So it looks like me in a 100-meter sprint, lightning out of there, massively quick, and then slowing down. A little bit exhausted maybe. What is the acceleration during the first second? So this is the first second. Again, I'm going to try and read off where 1 second is, which is awkward on this scale, but probably around about there. So it's gone from 0 to 5. So the change in y is 5, and it's 1 second. So 5 divided by 1 is 5 meters per second squared. Is the units for acceleration. You might know that from science, because I'm doing meters per second divided by seconds. So I'll move on to 6, because it's got quite an interesting bit here. Again, it's a speed time graph, so the change in the line is the acceleration. But again, it's got a terrible scale, going across in 5s like that. Hard to read off precisely. So give yourself a little bit of leeway when you look at the answers on the back. Anyway, describe the journey shown by this speed time graph. We're starting from 0, so we're starting by not going anywhere. starting at rest, as I say scientifically, and you're getting quicker and quicker and quicker until you get up to a speed of what looks to be 2 meters per second. And at that point, you do a constant acceleration until you get to a maximum speed of 4 meters per second. And from that point, after 5 seconds, you're slowing down until you come to rest, or 0 meters per second, in 15 seconds. So it's quite a precise explanation and description of the journey. And that's because we've got an A-level in physics. Hopefully you can pick out the bits that you think you need for that to give the sort of key one. And it'll be quite good on the exam question to look at how many marks are available, because remember, for each 1 mark you need to make 1 statement. Hopefully that's enough. As I say, this is a fair bit easier than most of the rest of the chapter, so maybe a little bit of light relief, but for me, I love the algebra, so I'd be happy doing that. Okay, thanks a lot. Bye.